Okay, welcome to section 2 of chapter 2, and we're going to talk about limits involving infinity. In this video, it's going to just be talking about this idea of horizontal asymptotes. Now, the definition of a horizontal asymptote is that the line y equals b, that's a y equals line, so it's horizontal, is going to be a horizontal asymptote of a function y if either of the following cases are true. That as you approach infinity, your function approaches a constant value that it can't seem to pass by. I'm going to draw that one. Right, there it is. And maybe your function just goes like this, and it just can't pass that constant value of b. We call that a horizontal asymptote. And the same is true if we're approaching a negative infinity, and I'm going to keep it right about the same here, but if we're approaching a negative infinity and your function hits a place where it just can't seem to get above it or below it, then that y equal b, whatever that y equals line is considered a horizontal asymptote. Keep in mind, it's kind of a myth in Algebra 2 and Pre-Calc, but the vertical asymptotes have to apply for the whole curve. You can never cross over a vertical asymptote, but that's not true with horizontal asymptotes. There's definitely, we could definitely have different circumstances here where you could have a horizontal asymptote that only applies to one part of a graph. But if it's a boundary for any part of the graph, it is considered a horizontal asymptote. Okay, so I'm going to put this in asterisks here. We're going to get this idea then that the limit as we approach an infinity, a positive or a negative, is really very similar to that idea in Algebra 2 and Pre-Calc of finding horizontal asymptotes. So let me go ahead and give you a couple examples of that. I think I have 3, and then one example and we're done. We'll get to the other type of limit at infinity, which is a vertical asymptote. So horizontal asymptotes first. Okay, we're going to find the limits. This is calc. Right here is calculus, finding limits. Right here is algebra 2. Okay, in algebra 2, if you were asked to find the horizontal asymptotes of this function, I believe what you typically did was you compared the powers in the bottom to the top, and you only looked at the highest powers. You never really bothered with all this other stuff. It was negligible. Some of you even went so far as to rewrite it as, well, I don't have any x to the thirds up here. I have 1x squared, 3x minus 7 all over 4x to the third plus 1. And you proceeded to ignore all this stuff and say, oh, I'll just make a fraction out of the coefficients. And you got 0 over 4, which is 0, and you said you had a horizontal asymptote was y equals 0. Okay, let's do calculus. The limit as x approaches infinity is 0 for the same reason, because the power in the top is smaller than the bottom. I want to get away from this having to write them both with the same to the same power. I don't know if anyone of you have ever even asked why you could just ignore all these terms. But I'll tell you, if you put these in your calculator, you'll kind of see. We're looking way out at infinity, okay? Way out at infinity, does plus 1 really matter? Or for that matter, does even a 3x minus 7 really matter? And the answer is no. If you're plugging in these huge, huge values, they call these terms negligible. And we look at just the term in the numerator denominator with the greatest magnitude. And this, anything to the third power grows a lot faster than those things to the second power. So we would say that this has a greater magnitude in the denominator. So what you end up with is small numbers over big numbers. And if you have numbers that are increasing very slowly, 1, 2, 3, 4, and you put them over denominators that are increasing even more rapidly, 3 over 1,000, 4 over 10,000, we can see that these numbers, as we get further and further out, are getting very small. And that's why the limit is 0. Okay, let's move to the next one. It's an algebra 2 question first, right over here. Find the horizontal asymptotes of this. And some of you would look at this and say, well, The x to the fourth has a bigger power, which is good. Some of you would even write it as this, which is, I'm hoping, not necessary soon. And you'd say, well, the magnitudes are now, the powers are the same. I'll make a fraction out of the coefficients, and you'll say, holy cow, 1 over 0. That means there's no horizontal asymptote, right? It's just 1 over 0. Picture this, 1 over super, super small. So instead of 0, I'm going to write a really small, small number. I don't even know what that is, too many zeros. But you can see when I multiply by the reciprocal, this thing is big, right? This is basically going to infinity. And we know that when a limit approaches infinity, we're going to say that it does not exist, all right? And I'm hoping that the process is you're saying, oh, this top is growing faster than the bottom. The top numbers are getting huge, 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 and the bottom aren't. Okay, and then let's go ahead and look at the last one. I believe in Algebra 2, most of you would say you have 1x to the third, and you'd ignore this other stuff. And you would say, well, I have the powers are equal. I'll make a fraction out of the coefficients. And that would be your horizontal asymptote would be at y equals 1/4. We're going to do the same thing, but we're not really, we're looking just to define the limit. And the limit in this case works the same way. If they have equal magnitude, they are going to approach a constant. That's not 0. And so we would want to say, sorry, that the limit equals 1/4. If you put this in your graphing calculator and you look way, way, way out, you will absolutely see this function start to level off at about 1/4. Please, please, please do that. Okay, so this idea of magnitude, which ones are growing faster and when they're growing the same, I'm going to just give us one example. In your homework, will have some others. But one example, it's not really a horizontal, it's looking at this idea, but I didn't give you just polynomial functions. In calculus, we're not just going to deal with x to the third, x to the fourth, and x squared. We've got these other functions thrown in. So if you're looking at this like, wow, I'm not sure how to use that idea of what's growing fastest, the top or the bottom, we can kind of look at just what's negligible. Out at infinity, sine isn't doing much at all, right? The values of sine are only between -1 and 1. So way out there at infinity, it doesn't much matter, what those values are. So we're going to call those negligible. We're literally just going to ignore the sine function. I know no one ever wants to do that, but that's what we're going to do. And then what we're going to notice is that we end up with this. I'm just ignoring it. You guys have been doing it for years. I'm just telling you why, because out at infinity, it doesn't amount to much. Now, when you get here, you can put that in your calculator, or we can just simplify it even further. I want you to picture the line y equals 5. Made it very easy for you, didn't I? Right? And way out when x is approaching infinity, way out here, infinity's right here, the value of y is going to be 5, and that's what our limit is. Okay? So you can use that idea of looking at the most powerful term. 5x is a line that has a slope of 5, and sine just bebops between -1 and 1. It just doesn't have great magnitude. So out at infinity, it doesn't really amount to a hill of beans. All right, folks, that's it.